Okay, hi. In this experiment, we are going to determine the concentration of some salt solutions by measuring their density. Specifically, we'll be determining the percent salt and the density of several standard saltwater solutions, creating a standard line, and using that to find the percent salt in a couple of unknown samples. So here's what we'll do. We'll measure the mass of 3 or 4 10 milliliter salt solutions and find the density of each sample. That's equal to the mass of the sample over the volume of the solution, which in each case should be more or less precisely 10 mLs. We'll then calculate the percent salt for each of those solutions, where that's the mass of the salt over the mass of the solution, times 100 to get a percent. Once we have those standard points, we can plot them to generate a line, which will look roughly like the line you see down here. And then if we have a couple of unknown samples, we should be able to plot them on their line. And if we know one thing, in this case, we'll measure the density. And from that, we should be able to figure out the percent salt by mass in each of those samples. I should point out that we won't be doing it by just drawing a line down and estimating, although we will estimate. We'll do it slightly more precise by using the equation for a line to get a more precise x-intercept, if you will, for each of the unknown samples to get the percent salt by mass. Let's take a look at the no-math way of doing it, which is pretty close to the way we'll be doing it. First, we get the density and percent salt of several solutions. We'll plot that to get 3 or 4 points. Then we'll measure the density of the unknown solutions, just like we said. Say one of them shows up here. You could then estimate that the percent salt by mass would be whatever that number is, say, I don't know, 10 or 15 percent by mass. Okay, to do it a little more precisely, we will use the equation for this standard line that we created. And the equation of a line is y equals mx plus b. Here it is rearranged to solve for x, where in this case, y is the density of the sample, m is the slope of that line, x is the percent salt in that sample, that's the x value there, and b would be the y-intercept, which is that value right there. Here it is rearranged. So if once you have one of these, you can calculate the other. So we'll create the pre-lab like we always do, include your tables, but don't forget to include the purpose and the signatures. I had to take points off for the last 2 labs because of that. Next thing, we'll create approximately 7, 14, and 21% salt solutions. And what I mean by that is we'll precisely measure their percent salt by mass, but each one should be in somewhere near 7, near 14, and near 21%. We'll also have a 0% solution, which is pure water. This is a 20-step procedure, and as usual, I don't want to read through each step, but just follow the instructions. You'll see everything gets done basically in triplicate. You generate some averages. It's fairly time-consuming, but in the end, you should have a nice standard line that you've generated on graph paper. This is not Vernier or computer-generated. This is old school, generating a curve on a straight line in this case, on a piece of graph paper. We'll then follow the steps in part 2 to measure the density of some unknown samples, in this case 2 commercial samples. You'll measure their densities, and so that you could see how you could at that point plot them on a line and have a good estimate of the percent salt by mass now that we have our standard line. But doing it a better way would be to solve for the percent salt, which is x, and here it is rearranged, so we should be able to do it more precisely, and that is part of the calculations. All right, a couple notes and specifically what calculations we're looking for. Each standard solution should be about, but not exactly, 7, 14, and 21% by mass. And this description of how to do that is outlined in the experimental procedures. When you're massing any of your solutions, do it while the cap is on to avoid evaporation during weighing. That's just a helpful detail. And when you have to determine the slope of this line, you don't have to use actual data points that you had. You could actually find 2 widely spaced points and simply do the rise over the run to get as precise as you can a value of the slope, which has the letter m in this equation. Here's the calculations we're looking for. There's 6 listed. Not all of them are exactly calculations, but here's what we'd like to see. For the 0%, that means pure water, 7, 14, and 21% salt solutions, calculate both the density and the precise percent salt for each. Generate a table if that's a handy way to do it, to show the calculations. calculate the average densities when it's necessary for those solutions, since you might be doing it in triplicate, as I pointed out before. Find the slope of the line, as we just indicated. Find the y-intercept. You could estimate it, and I'd recommend you do that, but solve for b, which is shown right there, to get a more precise value. Also, write down your unknown numbers, very important, no calculation there. And the big thing that we're looking for is find the percent salt in your two commercial samples. And in each case, percent salt is equal to x, which is can be rearranged from the equation for a line. Don't forget that you will be measuring the density of those samples, so you should have a very good idea of what the percent salt should be by simply drawing a line down and getting an estimate. So you should know if you're doing well by comparing your estimate to your real values. And as always, don't forget your post-lab questions. Okay, that's enough for now. If you have any questions, send me an email, and we'll see you soon.